Thank you. All right, good afternoon. Are there any questions you wish me to clarify before I proceed? Are there any questions? Okay, let me just quickly summarize what I had done in the morning. We had talked about perturbations, and it's a matter of calculating this quantity, to arrive at the equations of motion governing the perturbations. And we saw that the left and the right hand side can be decomposed in scalar vectors and tensors. These are scalar and vectors and tensors under transformations that are confined to the constant time plane, for instance. And there is a decomposition, decomposition theorem, which states that, the scalar perturbations on the left-hand side can be equated to the scalar perturbation on the right-hand side, and similarly with the vector and tensor perturbations. Our primary interest is, of course, are the scalar perturbations. And what we saw was as follows. There are 4 generic scalar perturbations that we can introduce, but there are 2 coordinate transformations that can be carried out involving scalars. There are 2 genuine scalar perturbations. You can either introduce all the scalar perturbations in the metric and construct what are called gauge invariant quantities. Remember, what are gauge transformations? Gauge transformations are coordinate transformations that preserve the fact that perturbations are small in the original coordinate system and the new coordinate system. You can either construct gauge invariant quantities and examine their evolution, or much simpler, we will choose to work in a specific gauge. And we will work in this popular gauge, okay, wherein what we'll focus on these 2 quantities, we are focusing on the scalar perturbations. And the metric was of the following form: ds squared is equal to 1 plus 2a dt squared, right, plus a square of t, 1 minus 2 psi delta ij dxi dxj. This quantity a and psi are the scalar and are the 2 scalar perturbations we have introduced. And they are inhomogeneous. That is, they depend on both space and time. And you need to calculate delta G mu nu. I wrote down in the morning the complete delta G mu that arises from this. And I also wrote delta T mu nu. Okay. And it's a matter of equating them. And what we saw was that if delta Tij was proportional to delta Ij, that is a situation where no anisotropic stresses are present, then we saw that A equal to psi, which I'm going to hereafter call as capital phi. And this is often referred to as the Bardian potential. One is interested in this because it's gauge invariant. You can construct a gauge invariant version, which in this gauge reduces to this. And what our goal is to arrive at the equations of motion governing the Bardian potential. Okay, so I'm going to write these equations again. 6h phi dot, right? I had written the left-hand side and the right-hand side. I'm just going to equate them. Plus h phi, shocks break easily. Okay, minus 2 by a square, nabla squared phi equal to minus 8 pi g delta rho. And then I'm going to use the third equation, the intermediate equation we don't need. Notice wherever I see a psi or a, I have set it equal to capital phi. Okay, plus 8h phi dot, okay, plus 2 times 2h dot plus 3h squared phi equal to 8 pi g delta. This is the 0, 0 equation, and this is the II equation. Remember, they contain delta rho and delta p. Okay. I'm going to define something called non-adiabatic pressure, which is defined as follows: delta p minus something is often denoted as CS squared or CA squared, where CS squared is P dot by rho dot. I presume you recognize the dots denote differentiation with respect to cosmic time t, okay? And P and rho are the background energy density and pressure. What we are focusing is at any given time, there is just one component of fluid, okay? And that is what we are focusing on. We are not accounting for multiple components when there are additional terms. We'll just focus on the simple case. At any given time, either during inflation or a radiation dominated era, there is one fluid that dominates the background and the perturbation. And so you combine these two, all right? And you can use the background Friedman equations to arrive at the following equation. There is a lot of algebra involved. I'm leaving all that for you to work out. If there are any questions you have about the algebra after you try, you are welcome to ask me. And I'm going to write hereafter in terms of a new variable I have already introduced. You know, t is cosmic time. And eta, remember, I introduced something called the conformal time coordinate. And remember, a d eta is dt. And hereafter, the primes that you will encounter that I will write down are represent differentiation with respect to this conformal time coordinate. So combining these two and using this relation, this equation, and this relation, you can arrive at this equation. CS squared script h, I will define what script h is, minus CS squared, nabla squared phi, okay? So what is script h? It's often referred to as the conformal Hubble parameter. Script h is equal to a times your standard Hubble parameter. Okay? Yes.
Like now we could have defined it like P over rho.
It's essentially dP by d rho, okay? But it is just involves the background quantities, they which depend only on time. And therefore, it is essentially P dot by rho dot. Yeah, it is delta P it's if it is adiabatic, okay, this will be CS squared will be dP by d rho, in which case delta PNA will be 0. Okay, yeah. So that's why if it is adiabatic, CS squared, this will be 0. Okay, if it is an adiabatic fluid, okay, then this will be 0, right? And for instance, what if P equal to W rho, where W is a constant, okay? So P by rho is, P dot by rho dot is P by rho, okay? And P by rho is W, okay? So delta P is W delta rho and it vanishes, okay? So you may have strange fluids where this is non-zero, but in simple cases, this non-adiabatic pressure vanishes, okay? All right, so let me summarize what I have done. It is the IJ equation and the 0, equation that I have combined to arrive at this Bardeen equation. And all I have done is that I converted, so if F dot is essentially F prime by A, and the primes here denote differentiation with respect to the cosmic time eta. Okay, so F prime is dF by d eta. Okay, actually partial derivative dF by d eta. Okay, is that clear? So so there was only one quantity that describes the scalar perturbations, and by combining the Einstein's equation judiciously, we have arrived at this equation, and this is what is known as the Bardeen equation. And this is what, cosmologists want, okay? They want what is the value of the Bardeen potential phi, okay, when the modes re-enter the Hubble radius. That I hope you have recognized. Your background is homogeneous and isotropic, correct? So I can write my solutions, and it's a linear differential equation with some source term, okay? So I can write my phi is a function of eta comma x, right? I can write this some integral d3k some phi k of eta, right, times e power ik dot x. This is what I have been repeatedly saying, right from day one. When I talk about perturbations, when I talk about modes, I'm talking about modes such as this corresponding to phi k, okay? This is a Fourier mode of the Bardeen potential phi. Because the background is homogeneous and isotropic, and I am focusing on linear perturbations, right? I have a linear differential equation, right? And I can Fourier decompose in this fashion and substitute in this. And you can convince yourself what will happen is that each of these modes phi k will satisfy this differential equation. All that will happen is that this nabla squared phi will be replaced by minus k squared, okay? So all I can do, I'm just going to write that here, phi k, not a vector k, okay? This actually, to be precise, has to be the vector k. But notice, this equation does not contain vector, it just contains k, okay? That is not surprising because the background, smooth universe, is isotropic. It cannot depend on k vector, okay? So I just have to replace this by plus k square, phi subscript k, and there should be, someone should provide me what is delta PNA of k. Okay, and it's a matter of solving this differential equation, that's it. Okay, so remember the picture that, we have been drawing repeatedly, okay, where we have drawn, the radiation dominated epoch and the matter dominated epoch, and these modes enter the, I have to do this slightly like that. Okay, the modes enter the Hubble radius at different epochs. Remember, this was what we refer to as, this is matter domination, this is radiation domination. We haven't yet talked about inflation. We are talking about, period when it is dominated by some hydrodynamical fluid, okay? And this, for instance, is your, evaluated today, of course, is your lambda EQ or KEQ. that enters at the epoch of radiation equality. So all I want is what will be the solution to this differential equation? What will be the Bardian potential? In fact, if late time cosmologists who want to study how structures form, for instance, all they want is the amplitude of the Bardian potential on super Hubble scales or at the time of re-entry. Is that clear? Okay. So we would like to know how the solutions to the Bardian potential, what are the solutions to the Bardian potential? Okay. It is, it is judicious, and in cases where I just argued if P equal to W rho, let us say in radiation or matter dominated epoch, okay, P equal to W rho is satisfied, delta PNA is 0. Okay, so which means the right hand side is 0, you just have to solve that differential equation. And what you do is that you carry out a suitable transformation and reduce it into a much simpler form, which resembles like a Schrodinger equation. I'll come to that in a minute. I will leave that whole thing as an exercise. Let me pull out this equation. Just bear with me. Right, I have the Bardian equation. Right. Okay, so I'm going to write a much simpler version of the Bardian equation. I'm going to define two new variables. One, which is U, which is, there is a subscript K everywhere. I'm going to suppress that. Well, I can write it, not a problem. Okay, phi. Now, remember, UK and phi K depend only on time. Okay, this is the quantity. The spatial dependence has gone away now. Okay, and I'm going to write this as phi K divided by square root of minus H dot. Okay, notice I'm mixing dots and primes, but you should be able to go from one to another. And I'm going to introduce another quantity. Just give me a minute, which is theta, which is H by A root H dot. In terms of these quantities, this differential equation can be reduced to this form. So it's lengthy algebra. I'm sure you will work it out, right? Let me write down the final equation. Is U, goodness. Let me grab another chalk, seems to be breaking. U double prime, UK double prime, plus K square, CS squared UK, plus 2H prime, plus 1 plus 3 CS squared H squared, plus half, goodness, minus H dot prime divided by minus H dot whole prime minus 1 over 4 H dot prime by minus H dot whole square. Okay, UK equal to 4 pi G A square minus H dot minus half delta P N A K. That's the expression you obtain after a lot of algebra. And it so happens this whole expression, this whole messy expression can be written in terms of theta in the following simple form. Right. So this is the Bardeen equation we are. So UK double prime plus K square CS square minus theta double prime by theta UK equal to 4 pi G, right hand side, A square minus H dot or minus half delta PNA. Okay, here's what we obtain. Where theta, I'm just going to write this here again. Theta is given by H by A root H dot. Okay, I hope I got that right. Yes. Okay, this is the equation. All right. And you can write this as, yeah, that's correct. Okay. Now, what we are going to do is as follows. Right. What we are going to do is as follows. What we are going to do is as follows. We are going to obtain what are known as super Hubble solutions. Right? So remember, where does the super Hubble or sub Hubble comes in? It depends on the value of K, right? And that has to be compared with this quantity. Remember the picture that we had earlier, okay? I erase this. I'm not able to retain that, okay? This is, thankfully, remember this mode, and there are other modes. This is the super Hubble solution. You can have a situation where this is entering here, okay? It can be super Hubble during the matter domination as well. And we would like to understand the behavior, the standard thing, logarithm of A, which we call as number of e-folds, and we are plotting essentially the Hubble radius and the physical wavelength. Okay? And one thing is super Hubble implies this is negligible, right? Remember, when the wavelengths are large, okay? When the wavelengths are large implies the K is very small. Is that clear? The wave number is 1 over the wavelength. And in such a situation, there are two solutions, okay? I'm just going to take a different set of chalks, just bear with me. Okay, so if you don't, if you ignore that term, so UK, well, it is no more dependent on K because you've thrown away the K dependence. Okay, so there is one solution for whatever reason. Everything is UK is proportional to theta. That's clear, right? What do you have? When delta PNA, I should write that clearly. So super Hubble modes, when delta PNA is negligible, 0, and K, squared CS squared is much, much smaller than theta double prime by theta. That's the domain we are interested in, okay? In that domain, what happens? Once you have this equation, UK double prime divided by UK equal to theta double prime by theta. So it's clear, one solution is UK is proportional to theta of eta. Right? What does theta depend on? What does theta depend on? It depends on this quantity. Okay? Do you know what it is in a radiation or matter dominated universe? Okay, you do know, right? So it can be written completely in terms of the background evolution. That's the point. Okay, and the other solution, this is one solution, and the other solution is what? UK 2, the second side. It's a second order differential equation. There is another solution, which I will let you convince yourself. It happens to be theta of eta, integral d till eta tilde divided by theta squared eta tilde up to eta. These are the two solutions. I will let you check, differentiate it and show that it's indeed a solution. So the most generic solution you have for UK is proportional to C1 of K, theta of eta, plus C2 of K, theta of, okay, I should write it the other way around, I'm sorry, because C1 and C2 have some meaning. D eta tilde divided by theta square of eta tilde plus C2 of K, theta of K. So if I'm during the early stages of the radiation dominated era, okay, all my modes are well outside the Hubble radius, okay, and I need to provide, where are the initial conditions buried? Where are the initial conditions on the perturbations buried? Imagine late time cosmologists who wants to study the imprints on the CMB, which emanates from around this regime, or the formation of structure. What do they want? In their equations, there will be a Bardeen potential that will appear. Okay, they will be interested in the evolution of matter perturbations, for instance, which means you will have an equation for delta rho, which I would urge you to arrive at, and that, as you can imagine, will depend on the Bardeen potential. They will ask, what is the Bardeen potential? How does it evolve? And we have seen on super Hubble scales, all the modes are at the super Hubble scales at early times. And we have seen that the super Hubble solution to the Bardeen equation can be easily written down, and it contains two quantities. Not surprising, it's a second order differential equation. You need to provide two initial conditions that will determine your C1 and C2K. Is there any universal form of C1 and K and C2K that we can provide? No, we cannot, because these modes are in super Hubble scales, and that's the whole idea of the horizon problem. And I don't know what C1K and C2K to provide. This is what essentially is the horizon problem is. The modes are outside the Hubble radius. I don't know what initial conditions to provide on the perturbations. That's why we need inflation. We need some quantum initial conditions, etc., that we will talk about. Okay, so now we have these solutions. Now the question is, are both these solutions allowed? Okay, are both these solutions allowed? Can you think about what will happen? Are both these solutions allowed? Are both these solutions allowed? Okay, so can you guess what may happen? Okay, let me proceed because I'm running behind schedule. Okay, so we are interested in A of eta, which are of this form. Just bear with me. Where is the A of eta written down? That's right. Proportional to some A equal to A naught eta power beta plus 1. Okay, I'm writing in this form for convenience. What is beta in radiation domination? 0, because A is proportional to eta in radiation domination, and in matter domination, eta squared, therefore beta is, so I can consider arbitrary beta. Okay, so you can construct theta. Okay, I will let you show that for such power law, theta happens to be, okay, I'm not going to fix this. Well, I have the exact relation, happens to be beta plus 1 by beta plus 2 into 1 over 8. This is theta. I will let you work it out. I have erased the form of theta. It's not difficult to work it out. And now remember, we are interested in phi, okay, phi subscript k. And there was a relation between phi k and uk. So I'm substituting all of it, and what I obtain is as follows. The solution for phi k of eta happens to be beta plus 2 by 2 beta plus 3 into C1 of k plus beta plus 1 by A naught squared C2 of k divided by eta power 2 beta plus 3. This is the complete solution. This is just evaluated here. That's all. Is that clear? So for power law expansion, we can obtain the solution to the Bardeen equation on super Hubble scales. Yes? Okay. Now, can you tell me something about the behavior of these functions? What is the range of eta in radiation and matter domination, early times to late times? Eta can go from 0 to some large values, right? Or some, in matter domination from some finite value to some large values. Okay. So what will happen to this at late times? It will decrease or increase? It will decrease. What is this? It's a constant. So there are two solutions. As you may have guessed, one will be growing and one will be decaying. Correct? So this is a decaying solution. As eta increases, this decreases. Well, the growing mode is not actually growing, it's a constant. So the Bardeen potential is a constant on super Hubble scales. Whether you are in radiation domination, I have again erased that picture. I presume that picture is imprinted on your mind now. On super Hubble scale, the Bardeen potential happens to be a constant. Now, do you foresee any problem with such a mode? What will happen as I go back in time? It will diverge. The decaying mode is extremely large at early times. That's unphysical. Okay. So I need to have initial conditions that does not permit C2 of k. That is not feasible. At very early times, it will be exceptionally large. So my solution is essentially this. And it is the C1 of k that has to be provided by inflation. Okay, that's all the story is. Okay, before we proceed, there is some, algebra I got to do and introduce a certain quantity, which I will use in the context of inflation. Let me introduce that quantity. Right? In fact, what I would urge you is that you go back to the Bardeen equation, assume delta PNA is 0, and actually solve for it exactly, right? In other words, rather than obtaining the solutions of the super Hubble regime, solve for it exactly. And from what my notes tell me is that the Bardeen equation can be solved exactly in terms of Bessel functions, either during the radiation and matter dominated epochs. I don't know, in some limits, it can be solved in both the epochs, even during the transition, etc. But you can write down the exact solutions, and I would urge you to construct that. But what one does is as follows. One constructs a conserved quantity, which is a quantity which is conserved on super Hubble scales. Okay. So again, I'm going to skip a lot of algebra. Okay. And just quote the results. I'm going to define some quantity psi. R is equal to psi plus h by rho plus p delta q. Okay. Remember, the psi was the quantity that appeared in the metric. Correct? What was delta q? Do you recall? It appeared in delta T0I. Delta T0I was di times delta q. So it is like the perturbation in the velocity potential flow. Right? If I have to construct a 3 velocity out of a scalar, I can operate the gradient and arrive at it. And this was the gradient. Okay. I'm sorry, this was the quantity that the gradient was operating on. And now you can make use of the zero I equation to rewrite in the form and so on, but I'm going to skip all that and show the following. You can write, okay, let me get my classes completely. You can take the time derivative of this R prime, okay, and show that this is an identity. H squared minus H prime 4 pi G A squared delta P and A, okay, plus C S squared nabla squared phi. This is what it is. This is an identity. Let me emphasize, this is an identity. Okay, I've already defined delta P and A for you. And now let us see what happens on super Hubble scales. If you have delta P and A to be zero, in the case of fluids that we have been considering, what will happen on super Hubble scales to this quantity? What will happen to super Hubble scales on this quantity? So this will be minus K squared, correct? And this will be delta P and A of K, and this will be the kth mode, Rk prime. Okay, I've just defined some quantity here. Now, what happens if this is zero or negligible? On super Hubble scales, this will be negligible, and therefore R prime will be zero. So there is a quantity R which is conserved on super Hubble scales. And this quantity is often referred to, Rk is referred to as the curvature perturbation. Because what happens, you had a background which was spatially flat, but you have introduced inhomogeneities. Therefore, there is no spatial flatness anymore. I hope it is clear. We had a spatially flat, homogeneous and isotropic background, but we have introduced inhomogeneities on top, and these inhomogeneities are changing the curvature, and the curvature at any given point is proportional to Rk. Again, I would urge you to show that. Take the original metric, calculate the curvature associated with the 3 metric, and show it is proportional to the R that is defined here. Okay, so, and for this reason, it's always referred to as the curvature perturbation. And what happens to the curvature perturbation on super Hubble scales? It is conserved. This is the point. And this conservation of the curvature perturbation on super Hubble scales, okay, can be used to relate the primordial perturbation with the perturbations at later times. That's the point. Okay, so if I draw this picture again, here we have inflation and radiation domination, and then inflation here, and a mode leaves the Hubble radius. So if I know what is the curvature perturbation at late times here, when the mode is well outside the Hubble radius, I know the curvature perturbation at the time of re-entry. Okay, and the Bardeen potential is also constant on super Hubble scales, so you can relate them. And if the late time cosmologists want the Bardeen potential, you can provide that as well. You can use conservation of curvature perturbation to relate the Bardeen potential at early and late times. So our goal now is, we have seen how the perturbations, scalar perturbations evolve. We are focused, as far as the early time physics is concerned, focused on the evolution of one quantity, which is the Bardeen potential. Okay, and in fact, it seems more suitable to understand the evolution of the curvature perturbation. So now, until now, we have been talking about the perturbations here, right? You know, what we would like to know is, how are they generated at early times during inflation? What do we need to do now? All that we need to calculate is, can someone help me? What is that we need to calculate? Say that again. That is correct. We need to eventually arrive at C1. Okay, C1 of K can be used from arrived at from the conservation of the curvature perturbation, right? But you know, to arrive at the, but I need to study them during inflation when the scalar field is dominant. So I need to set up this perturbation theory when the scalar field is dominant and there are perturbations in the scalar field. I'm assuming that there is no other fluids present during inflation. Remember, the dominant field is that of the scalar field, and that is what is driving inflation. So all I need to do is calculate essentially the stress energy tensor associated with the scalar field, okay? Or in other words, I need to calculate delta rho, delta P, and delta Q for the scalar field, okay? Plug in my equations and arrive at the equation governing the curvature perturbation. That's all there is to it, okay? So I go back to my stress energy tensor of the scalar field and ask what are delta P and delta rho associated with the scalar field. Okay. I need to open another notes. So we are going to talk about generation of perturbations. So why are we interested in the perturbations during inflation? Because these modes will be inside the Hubble radius and we will impose what are the correct initial conditions. In some sense, as someone said, we need to determine what is C1 of K. Something like mod square of that is the power spectrum, what we will define as the power spectrum associated with the scalar perturbations. Okay. So, generation of perturbations. So we are interested in scalar field dominated inflation, right? We already seen the action governing the scalar field. You know how to construct the stress energy tensor, right? S of phi. I had written this action earlier. It is integral d4x root minus g half d mu phi d mu phi d mu phi minus v of phi. And the stress energy tensor T mu nu happens to be d mu phi minus g mu nu half d mu phi or d lambda phi d lambda phi minus v of phi. All this we did. Now we need to go ahead and construct the, oops, what is going on here? Sorry, something. Sorry, I'm having some difficulty where my pages are not turning. Yes. Okay. So you need to construct the perturbations in the perturbed stress energy tensor. I'm going to write the components here. Remember, delta T00 is minus delta rho, happens to be phi dot, delta phi dot. I hope it's clear. Delta phi dot is the perturbation in the scalar field. All you need to do is take phi to be phi plus phi dot and g mu nu to be g mu nu plus delta g mu nu and construct this quantity. And as I already mentioned, it will contain the metric perturbation as well, plus a phi dot squared minus v phi delta phi. Delta T0I is minus di phi dot delta phi. Remember, I mentioned this already. Okay, if you recall, in the case of fluid, this was of the form delta T0I is equal to minus di delta Q. And delta Q, there is nothing else present, only delta phi present, and it has to be constructed out of that. Okay, and then the other point I mentioned is delta Tij is equal to phi dot delta phi dot minus a phi dot square minus v phi delta phi delta ij. What does it imply? Remember, when I wrote down the delta Tij for fluids, I said that can be something called anisotropic stress in the case of fluids. We considered a situation where the anisotropic stresses were absent, but in the case of scalar field, the anisotropic stresses are naturally absent. Okay, that's it. It's a matter of taking these equations and plugging it in the equation of motion and arriving at the in the first order Einstein's equations and judiciously mixing them up and arriving at a second order differential equation for RK. That's what we are interested in. Okay, all right. So I'll just indicate a few steps before I go on to write down the solution. To write down the complete equation. So just keep a note. For want of space, I'm not able to retain that equation for R prime, okay, RK prime. Please keep it somewhere and you can arrive at the Bardeen equation. This is the Bardeen equation, but you know how to do. You just have to mix the 0, 0 and the ij components. And what you obtain is as follows. Phi double prime plus 6h phi prime plus 4h squared plus 2h prime phi, right? Okay, minus nabla square phi equal to minus 8 pi g a square v phi delta phi. Okay, this is the equation, right? Okay. And actually, I should write it in a slightly different form. Okay, this is an intermediate step. The final step is as follows. I can write this as 3h 1 plus ca squared phi prime, okay, plus 2h prime plus 1 plus 3. The reason for writing in this form will become evident very soon. Phi squared phi, okay, minus nabla squared phi equal to 0. Okay, all right. If you compare, now what I'm going to do is that I'm going to write this as minus ca squared nabla squared phi, right? This is the equation. Let me just, maybe I should comment about it before I say additional remarks. This is the Bardeen equation. I just have rewritten this. Why have I done so? So that it can be compared with the equation we obtained in the case of fluids. Look at the equation we had obtained in the case of fluids. Everything is the same, modulo this term and the term on the right hand side. This term had a factor of ca squared, okay, and the right hand side contained a delta PNA. Okay, but then I can easily do that. I can add and subtract ca squared nabla squared phi, okay, and I can subtract minus ca squared nabla squared phi. I can take this to the right hand side, minus nabla squared phi, which implies this is minus becomes plus 1 minus ca squared nabla squared phi. Is that correct? Okay. So now what do we got now? Can you tell me what have we got? Ca squared, I have used the term Ca squared. It is actually in my earlier board, I think I used the notation Cs squared. Okay, I'm sorry about that. I should have written Cs squared. It's just what I use in different papers, that's all. Cs squared. It's just P dot by rho dot. You know what is P dot? P and rho in the case of scalar field, it was phi dot squared minus V and P was phi dot squared minus V and rho was phi dot squared plus V. And you can use them to arrive at P dot and rho dot. This is what it is. So what have we learned? What have we learned from this? We know what is delta P and A for the case of a scalar field. It's non-zero. It's given by this expression. But what is interesting is that look at the expression. Unfortunately, I have erased the R prime. Okay. Just, in the earlier page, you should have an expression for RK prime. On the right-hand side, it contained two terms. One was the nabla squared phi, and another was delta PNA. But now, what do we find here? The delta PNA is also proportional to nabla squared phi in the case of a scalar field. So during inflation, the RK is essentially proportional, RK prime rather, is proportional to nabla squared phi. What it implies is that on super Hubble scales means nabla squared phi is proportional to k squared phi can be ignored, and RK prime is a constant. If you recall in my overview talk, I emphasized, I highlighted this point as to how the perturbations are generated and they oscillate when they are inside the Hubble radius. On super Hubble scales, the perturbations freeze. And when I say those perturbations, I'm referring to the curvature perturbation, whose expression I wrote down in the earlier board. Okay? So why do they freeze on super Hubble scales? Because RK prime is proportional to k squared phi k. On super Hubble scales, they are ignorable, and therefore, they are conserved. Now, what we need is actually a full-fledged differential equation for R prime, or a second order differential equation for RK prime, which is what we will choose to integrate. I'm sorry, yes, we will choose to integrate, and we will impose initial conditions on RK prime, RK, or equivalently a related variable, something called the Mukhanov-Sasaki variable. I will introduce all of them in a matter of few minutes. So what we have is as follows. In the case, so if I take this differential equation for the Bardeen potential and plug it in the equation for R, I obtain the following. I obtain that, okay, R prime. This is during inflation. R prime equal to script h divided by script h squared minus h prime, okay, into 1 minus Ca squared nabla squared phi, right, plus Ca squared nabla squared phi, right? Evidently, this cancels, right? This cancels, leaving behind this term is equal to h by h squared minus h prime nabla squared phi. That's what you have. Okay. Now, what we would like to do is, there is a Bardeen potential on the right-hand side, okay, and a curvature perturbation on the left-hand side, and we would like to, arrive at a differential equations purely involving R, okay? So, we would like to use the perturbation equations to arrive at an equation of motion for the curvature perturbation. All right. So there is a minus sign I have. Okay, just bear with me. No, it's fine. It's correct. Okay. So I go back to my original definition of R. Okay. It happens to be the following. Okay. Remember, it was a linear combination of phi and, if you look at your notes, it was a linear combination of phi and delta Q. Just go a few slides back, okay? And now delta Q can be, where did the delta Q appear, if you recall? It appeared in the 0I equation, Einstein equation. And we have, in the case of the scalar fields, the anisotropic stress was 0. So, A is equal to psi, which we have called as phi. There is only one perturbation variable. Using these relations, you can obtain this equation for 2 rho by 3 script H into rho plus P into phi prime plus script H phi. Okay, this is what it is. Now I'm going to define a quantity which is called Z is equal to A prime by script H. Okay, very much like the manner in which we define theta, correct? I'm defining another quantity Z. Okay, and I'm going to take R prime and I'm going to take R double prime and I use the Bardeen equation. Okay, and use the Bardeen equation. And of course, the definition of R and Z that I have here. When I do that, you will arrive at this famous equation of motion governing the curvature perturbation. In Fourier space, Rk prime plus k square Rk equal to 0. There is a lot of intermediate algebra involved. I don't want to spend time doing the algebra, but it is important you spend time doing that. Otherwise, you will not be able to appreciate all the intermediate assumptions and steps that have gone in. But there is nothing more to it actually. If you are, if you are smart enough handling things like Mathematica, you can get it done with Mathematica. Okay, but that's all there is to it. So you have defined R, and you, for convenience, you define Z, right? And and I should mention that this is equal to also A phi dot by H. Phi prime is A phi dot, right? And script H is A capital H, and therefore it is A phi dot H. Remember that. Okay, all right? And that's all there is to it. But again, as in the case of the Bardeen potential, remember we had a phi k we needed to solve for, okay? But we reduced it to a equation that resembled the Schrodinger equation by introducing a quantity called theta, okay? It's essentially, when I mean a Schrodinger equation, I'm referring to a second order differential equation without the, dy by dx kind of term, okay? The reason is that I can compare with the Schrodinger equation and arrive at solutions. So you define something called the Mukhanov-Sasaki variable. Right? Okay, so what do you have? It is defined as Vk equal to Rk times Z. Okay, or Rk equal to Vk divided by Z. You plug it into this, just like there was a differential equation for Uk. The phi contain phi prime and other messy terms and so on, but you could arrive at a simple differential equation for Uk in terms of theta. Remember, we wrote down the solution for Uk in terms of theta. There was a growing mode, there was a decaying mode. It just allowed us to nicely write down the solution, okay? So what you obtain is that this is a simple exercise which you can do. You obtain the differential equation to be of this, where Z, I'm repeating, is A phi dot by H. This is the equation governing the scalar perturbations that you will often see people quote. Let me summarize. If you have understood the morning lecture, the spirit of the morning lecture, you should be able to what we have done this afternoon. Let's see where we started. We started by, after we had arrived at the Bardeen equation, and we constructed the solutions to the Bardeen equation in the super-Hubble scales. Why? Because that is the kind of initial conditions that late-time cosmologists need to evolve, say, understand how structures form, or even what are the imprints on the CMB. And we saw on super-Hubble scales, the Bardeen equation is a second-order differential equation. And if, in a radiation or matter-dominated universe, the solution, generic solution, contained two terms, one which was a growing mode and another is a decaying mode. The growing mode was a constant. In other words, the Bardeen potential is conserved on super Hubble scales. It changes its value only as it jumps from radiation to matter-dominated era or during inflation to radiation domination. And using this, and we threw away the decaying mode because if we retain that, that is not possible. The perturbations will be extremely large at early times, though it is unsustainable. So there was the C1 of K, or I will denote it as CG of K, G referring to the growing mode that we need to determine. Okay, that's all you need to provide. At different, what is the power in phi K, phi subscript K, at different wave numbers? That's what we need to provide. And those are the initial conditions to your differential equation. And conventional hot Big Bang model cannot provide that because those modes are on super Hubble scales. I don't know what natural initial conditions to impose. This was the challenge. That's what we discussed, the horizon problem. Here it was clearly illustrated, explicitly illustrated. So we turn to inflation. During inflation, we have a single scalar field driven inflation, canonical scalar field driven inflation. And the scalar field contains a perturbation, delta phi, correct? And we compared with the equations that, compared with the equations of fluids, and we saw that we could easily read off what is delta PNA is. And therefore, we could construct what R was, okay, the curvature perturbation. Why were we interested in R? Because whether it is on super Hubble scales, when it is dominated by fluids, when the universe is dominated by fluids like radiation or matter, R is conserved on super Hubble scales. Is that clear? So if I calculate R at the end of inflation, its value will be the same at the time of Hubble entry, whether it is during radiation or matter domination. Now, but we want to know what R is. R is conserved on super Hubble scales, but during inflation, it emerges from the sub-Hubble regime. So I need to impose some initial conditions. I know its amplitude will freeze on super Hubble scales, okay? And I can use that to, provide power spectra for people who calculate CMB anisotropies or the distribution of large-scale structure. So in order to do that, I need to arrive at a differential equation governing R, the curvature perturbation. All I need is the Bardeen potential and the definition of R. For convenience, just like I introduced a quantity called theta to understand the evolution of the Bardeen potential, I introduced this often called the pump field or something called Z, okay, which is A phi dot by H. It depends on the background quantities, as you can imagine. Remember, theta was just dependent on the background, if you recall. So in principle, if you provide me A of P, I know all of this, okay? So, and I arrive at a differential equation of this form. Okay, and what you do is you define a new variable. Okay, I will try to motivate this variable in a matter of minutes, just bear with me. You introduce something popularly known as the Mukhanov-Sasaki variable, V subscript K, which is essentially RK is a ratio of VK to divided by Z. Okay, and when you substitute that definition in that equation, you arrive at this equation, which is, for evident reasons, called the Mukhanov-Sasaki equation. Now, do you know what is the solution to Vk on super Hubble scales? Do you know what is the solution to Vk on super Hubble scales? Can you write it in terms of Z? You can, right? What is Vk? If super Hubble scales corresponds to the scenario where you, or rather not the scenario, the domain where you ignore K squared. When I ignore K squared, one solution is evident. What is that? Vk is Z. And what happens to Rk when Vk is proportional to Z? And that's the constant mode we will be picking up. The other one will be that will go away. That will not be important for us. Okay, now it's a question of how do I impose initial conditions on this. I have a second order differential equation All that has happened is that the C1 of K that you had at later epochs has been transferred to what should be the C1 of K at earlier times during inflation. Okay. Now I need to ask what should be the initial conditions on these perturbations. Okay. And what we will do is that we have said, okay, we have said that, well, I have said earlier in the overview that the perturbations are generated due to quantum fluctuations. Where are the fluctuations buried? In the scalar field. What do we refer to the perturbation as? Delta phi. Okay. Remember, this is proportional to delta phi. Okay. That's proportional to delta phi. And that's the perturbations which are inducing, those are the fluctuations that are inducing the perturbations in the scalar field. So what we will do is that we will elevate Vk to be an operator. We will treat delta phi to be a quantum operator, or to be precise, we will treat Vk itself or Rk as a quantum operator. And what we are interested in is the 2-point correlation function in Fourier space of Rk. Okay, and that is what is usually defined as the scalar power spectrum. And that, as you may have imagined, will essentially involve mod Vk squared by Z squared or mod Rk squared. That's what it is. So I need to choose some initial conditions on this and evolve these perturbations and evaluate the spectrum on superable scales. I'm just going to take the liberty of taking a few more minutes to illustrate what does it mean to quantize this V of K. So you would have done quantum field theory. Often you would have done quantum field theory in flat space-time most of the time. Okay, but you can do quantum field theory in a Friedmann universe. Okay, so what do you have? Let us say my field is chi. I've used a phi, I have used a psi, so some chi is some field. Okay, it's a massless scalar field. So what will be the action? Integral d4x root minus g. What will it be? D mu chi half d mu chi d mu chi. That's what it is. Okay, what will be the equation of motion? Sorry? That's just a name. Tell me what will be the equation of motion. So you will obtain chi box. I'm going to solve this in a Friedmann metric, flat Friedmann metric. ds squared is minus dt squared plus a square of t dx squared. Okay. Assume chi k equal to chi k of eta equal to some uk of eta by a of eta, e power ik dot x. Right? I'm trying to solve this. Once I solve it, I can quantize the field. Right? I mean, what do you do in Minkowski space-time? You obtain the modes and write them ak, one mode function plus ak dagger, the complex conjugate of the mode function. That's and sum over all the modes. That's what how you quantize. So if I have a quantum field in a Friedmann universe, I can quantize in the same manner. Okay. So notice I have written chi k as uk by a eta. I presume you recognize eta as my conformal time coordinate, which means I can pull out a square of eta and write this. Okay, do this exercise if you're not familiar with it. And since the background is homogeneous and isotropic, the modes can be decomposed as e power ik dot x. Is that clear? So do you know what's the equation of motion for chi k or uk rather? It happens to be the following. Okay. Notice the similarity between this equation on the left-hand side and the quantity Vk on the right-hand side. Okay. So in some sense, it is very similar to quantizing like a massless scalar field in a Friedmann universe. It is just that you have z double prime by z instead of a double prime by a. In fact, later, when we discuss quantization of tensor perturbations, we'll find that the Mukana-Sasaki variable of the tensor perturbation will be exactly of this form. Okay, we'll see that. So I hope I have tried to justify why I can quantize the field. When I quantize the field, what do? One of the important parts of the quantization is identifying something known as the positive frequency mode. Okay, in Minkowski, it's trivial. If you go, I know you read up about what is defined as a positive frequency mode, why the e power minus coefficient of AK, or rather e power minus I omega t is chosen to be the annihilation operator. Okay, all right. Okay, so you identify something known as a positive frequency mode because that identification, right, allows you to define a vacuum as A K operating on some vacuum state equal to 0. So in the context of inflation, what happens is that you are in a domain, the super Hubble domain corresponds to where this was negligible. As you may guess, the sub-Hubble regime. Remember, I kept promising you that when the modes are inside the Hubble radius, I have a causally connected regime. Okay? So when this is dominant and that is ignorable, what are the solutions? E power plus or minus ik eta. And I can choose my solution to be e power minus ik eta at early times and choose its coefficient on quantization to be the annihilation operator. Define a vacuum which is annihilated by that operator, and that's referred to as the Bunch-Davies vacuum. Okay, and I will evaluate the 2-point correlation functions in that vacuum state. Okay, so once it's a matter of being able to calculate the power spectrum from those initial conditions. And we will try to calculate the power spectrum. I'm a little behind, but I think I should be able to somehow catch up. Okay, we'll calculate the power spectrum in power law inflation. Okay, and we'll calculate the power spectrum in slow roll inflation. Okay, so let's consider power law inflation. Do you recall how H behaves as a function of cosmic time in power law inflation? Someone? A is T power P, T power Q. What is H? Loudly. H behaves in power law inflation as 1 over T. And do you recall we obtain phi of T in power law inflation? If you have scribbled in your notes, you should be able to find out. It goes as 1 over T. Okay? So in power law inflation, Z is proportional to A, and we can easily obtain solutions. Okay? Slow roll inflation requires a little more effort. We'll come to that. With those remarks, I'm sorry for taking a few minutes longer. I'll stop here. I'll be glad to answer a couple of questions before we break for coffee. Yes, stop.
What is permission?
Can you repeat the question on the microphone for the benefit of others?
What is the meaning of curvature perturbation?
So we will, you would have seen on super Hubble scales, the Bardeen potential and the curvature perturbation are related. They are of the same order. Okay. So it is easy to impose initial conditions on the Mukhanov-Sasaki variable or equivalently on the curvature perturbation. What does curvature perturbation reflect? Okay, it reflects, as I already mentioned, remember, the background is a spatially flat, homogeneous and isotropic Friedmann universe. The curvature perturbation tells you how much is the spatial curvature at any given point in space, at any time. And cosmologists essentially require the spectrum of late time cosmologists require what they refer to as the scalar power spectrum. Modulo factors of K is essentially mod phi subscript K squared, phi being the Bardeen potential. Okay, and I have erased the definition of A. You look at it on super Hubble scales, phi prime is 0. So R is modulo constants, it's like phi.
We started off with the assumption that it is already flat, right? Spatially flat, and this
That is correct, but there are inhomogeneities, right?
Okay.
There are perturbations. It's flat, but you want perturbations to be generated, right? But if there are inhomogeneities, which means there are differences, and the differences means there is non-zero spatial curvature, and that's what it reflects. The background, the smooth part is homogeneous. On top of it, there are small perturbations. Think of a, rubber sheet slightly wrinkled. That's what it is. Any other questions from here? Raga, any questions?
Just one question. In some books, they define curvature perturbation as psi equal to t plus 1/3 nabla square E in scalar metric perturbation. Is it related to the R curvature perturbation?
So I need to look at, there are two, there is another quantity which is zeta that is defined as well often, okay? And they differ, they are the same on super Hubble scales. If I recall correct, they differ by a nabla squared factor, and therefore they are the same on super Hubble scales.
And there is a question about references. We will be sharing the references that you have already provided
Absolutely.
soon to the participants, all participants, both online and offline. Thanks.
Thank you, Raga. Thank you, everyone.